discuss every single activity in this exercise, it will focus on explaining a few key concepts and tasks. Read through the entire lab exercise chapter before you watch the tutorial so that you can make sense of it. Make a note of any questions that you have, and if they have not been answered after you watch the video, bring them up with your instructors and fellow students in class or via class discussion boards or email. Welcome to the laboratory portion of your introductory astronomy course. This first laboratory exercise will serve as an introduction to the full sequence of labs for this course. The experiment and analysis you are about to embark upon may not seem to have much to do with astronomy, but they will give you a crucial background for succeeding in later labs. In this lab, you will explore proper techniques for obtaining and analyzing data, and you will receive direct training in using tools for plotting and understanding data. You will have a chance to plan a short experiment, make observations, and collect data for yourself, and you will also work with more complicated data sets that have been collected in advance by others. By learning basic techniques now, you will be able to focus on astronomy and science concepts and better understand the universe surrounding you when we take a second look later. You will need the following items to perform a simple experiment: either a half cup of pinto beans, a bag of marshmallows, several handfuls of gravel, 30 bushes or trees, a herd of amiable dairy cows, access to a parking lot full of cars, a few shelves of books, 30 friendly people, 2 bags of tortilla chips, or 30 coins of a single denomination. You will also need appropriate tools for measurement, such as a ruler, a tape measure, string, a stopwatch, and/or a kitchen or jeweler's scale. You will not need all of these items. You will select a particular experiment based on your interests and the materials you have available to you. For certain experiments, you may find a friendly assistant, one with no particular training but who is careful, to be very helpful.
Thanks again for agreeing to help me with this project.
Of course.
You will also need a computer with an internet connection to analyze the data you collect from your experiment. This lab is built around 4 activities. 1. Planning and conducting a short experiment with common household items. 2. Examining existing data to uncover a basic connection between seasonal changes and the height of the sun in the sky at noon. 3. Analyzing data, including error estimates. And 4. Making appropriate conclusions based on evidence. As a part of your laboratory exercises for this class, you will be writing a series of laboratory reports. These will be created and delivered through Google Documents applications, a set of online tools which allow you to write reports including figures and tables, make simple drawings, and share your work with others, available online. You will create for yourself a free online Google account for use in this course. If you already have an account, you may of course use it for this purpose. Once you have done so, you may return to the GEAS Project Lab URL, click on the URL labeled Google Doc Report Template for this lab exercise, and save a copy of the report template to your own Google Documents account. This file will initially be called Copy of Chapter 01, but go ahead and rename it for simplicity. Define a name by combining your last name and first and middle initials, followed by the phrase 01 to indicate that this is your first lab report. If your name is Cecilia Helena Payne, for example, call your file Payne CH01, keeping all letters lowercase. This will help your instructors to keep track of your file in a sea of similar reports from other students. To the right of the file name, you will see a small image of a lock and the words "Private to only me." Click on this phrase and grant permission to your instructors to both view and edit your file by typing their email addresses into the text box labeled Add People and selecting the phrase Can Edit to the right of the box. Make sure the checkbox next to the phrase Send Email Notifications is checked as you do so that your instructors will know that you've done so. Add their email addresses now so that they can verify that you have successfully set up your first lab report. You will be writing text and adding figures and tables of data within this lab report. As your instructors are also able to read and edit it, they will be able to respond to what you write and to leave you notes in the file. These can be viewed in a different color than your work. Start working on your report early during each lab exercise so that you have a chance to interact with your instructors about your presentation and results and can improve them before your lab exercise receives a final grade. Begin by selecting a simple experiment, one that we can do with common household objects in a fairly short amount of time. To keep things simple, we will choose a single property to measure, make a series of repeated measurements, and then analyze the distribution of those values. Before beginning your experiment, make a guess about what your results will be. Select one question from this list. You will make a series of 30 measurements in order to study the question. 1. How much do individual pinto beans or pieces of gravel weigh? 2. How large are the diameters of tree trunks or bushes? 3. How far can marshmallows be thrown? 4. What is the point-to-point length of tortilla chips? 5. How many pages make a book, or how wide or heavy are books? 6. How much milk do dairy cows produce per day? 7. How wide are windshields, or how large are tires? 8. What is the distance between the pupils of people's eyes?
I'd say 1.5.
You can't measure the baby. It's going to skew the results.
9. How long does it take you to complete a practice self-review quiz for this class? 10. How heavy or thick are coins of a given value? Each of these questions can be answered by conducting an experiment and making a particular measurement repeatedly. In each case, we will need to carefully define the process by which data are collected, collect data in a uniform and non-biased fashion, and consider the precision of our measurement technique. We will describe the distribution of values for the measured quantity by estimating two numbers, the mean or average value, and the spread or width of the distribution around the mean, how close most measured values lie to the mean. Once you have selected a question to answer, you need to plan your experiment. Determine that you have the materials necessary, such as a bag of marshmallows and a tape measure, and a clean, safe location in which to work. Think carefully about the process by which you will select the sample of objects to study and how you will make the measurements. Consider how precise your measurement tool is and whether this will provide you with an acceptable precision in making measurements. A good rule of thumb is if you are unsure that your measurement should be accurate to at least 1 part in 100. If you are measuring a length of 10 centimeters, you should record your data to at least 1/10 of a centimeter, and ideally to a smaller length. In your lab report, carefully describe your experimental plan. Give enough details so that if another student read your notes, he or she could duplicate your efforts in a consistent fashion and obtain a data set that you could use productively in combination with your own data. Later on, you will partner with another student and attempt to reproduce each other's results. Include a rough guess for the average value that you expect to measure. Keep it simple and remember that you are simply guessing, in part to select an appropriate measuring tool. There are no wrong answers to this question. Now that you have a plan, it's time to go ahead and start taking data. You will start by taking a small amount of data, performing a rough analysis, and checking that your results make sense. You will then complete the data set. If necessary, you will modify your technique for the larger set of data. As a first step, perform your measurement 7 times and enter the values into the second column of Table 2.
That was our last one. Those are 7.
Oh, okay.
Measurement time.
All right.
In the table title, after the words Experimental Data 1, describe the quantity that you are measuring, and in the column heading for column 2, after the word Value, state the units of the recorded values within the parentheses. You will transfer this information later into your online lab report, but it is probably easiest to first record the data on paper so that you don't need to have a computer handy as you conduct the experiment. You may, however, work directly on the lab report template if you wish. The word trial tells us that we are going to perform the same measurement repeatedly. It is important to be careful, to use the same technique, and to make the measurement to the same level of precision each time. We are trying to sample the underlying distribution of a large number of objects, but taking only a few measurements. It is thus important to sample as randomly as possible for the set of objects. Once you have measured 7 objects from your data set, stop and perform an initial data analysis on this sample. We want to determine the average value of the measurement and how widely the measurement varies over the entire sample. Consult your lab manual for instructions on how to do these calculations. Your lab manual will introduce the concept of a mean value, mu, and of the spread of the distribution, sigma, also called the standard deviation. The mean value is simply the average of all measurements. If the weights measured from 7 trials were as follows, then the mean value is simply as follows, where the summation symbol means that we are adding together the 7 measurements, as I runs from 1 to n, and n is 7 because we have 7 measurements. Putting in the measurements of the 7 individual measurements, we next want to know how wide the scatter is in values. Are most pinto beans within 1/10 of a gram or within 10 grams of the mean value? To find this out, we will calculate the spread, or the standard deviation. Consult your lab manual for instructions in making these calculations.
How are you doing on writing up that lab report?
I'm confused. We went out and threw all those marshmallows, but now it's asking me for pinto bean weights. I don't work with pinto beans.
Well, what does it say in the lab manual chapter?
It's got a good anecdote, and
The lab report isn't going to make much sense without the chapter. See? This question is asking about the example discussed on pages 8 through 10. See? We did a whole sample exercise using pinto bean weights as the example data. And now, the lab report is checking that you understood it. And that you read it.
I get it now. Thank you.
After you have worked with some sample histograms, it's time to build one for the 7 data points that you collected in Table 1.2. Reload the GEAS Lab web page and click on the link labeled Web Application Number 2, Plotting Tool. We are going to create a histogram plot from your 7 measurements. Begin by selecting Histogram at the top of the form from the pull-down list. Next, type in a title for your plot and labels for the X and Y axes. These labels should clearly identify the contents and purpose of the plot that you're creating. If you were measuring dairy cow output, for example, you might type a title of Dairy Cow Daily Milk Production and use X and Y axes labels of Amount of Milk per Cow, liters, and Counts. Be careful not to reverse the X and Y axes labels. The X-axis identifies the quantity being measured and its units, while the Y-axis tells us how many data points fall within each bin along the X-axis. Scroll down until you see the text box labeled Numbers to Plot, and enter your 7 measurements into the box, 1 measurement per line. Don't add any commas, parentheses, or other extra characters. Just type each measurement on a separate line. Once you've completed these steps, click on the button Create Plot, and your plot should appear in a separate browser window. Does the histogram appear as you expected it to look? A title should appear above the plot explaining its topic, and the X and Y axes should be clearly labeled. Your plot should show a histogram drawn as a series of light blue columns. Above the columns, the mean and sigma values will appear, labeled as mean value of mu plus or minus sigma. Now click on the back button of your browser to return to the plotting tool. Remove your highest and lowest measured values from the set of 7 and remake your histogram. You may need to retype your ID code to regain access to the database. Now do the same with your larger data set of 30 measurements. Copy the JPEG format plot to disk or email it to yourself and include it in your Google Document Lab report. An important part of conducting a successful experiment is being able to describe it clearly and accurately, so well that another person could read your description and then conduct a successful second set of trials. In order to test how well you defined your simple experiment, your instructor will give your experimental description to another student and give you their description of their experiment in return.
So, are you serious when you said we'd be throwing marshmallows?
See, the point of this part of the lab is to do the exact same experiment as somebody else in the class. Then they tell you what they did and you replicate it. The girl that I got paired with threw marshmallows as her experiment.
So what you're saying is that we need to throw marshmallows the same way she did?
Exactly.
Sounds great.
Okay, so I'm going to throw these and you measure from where I throw them to where they land.
Okay, I'm ready. Is that as far as you can throw them? I mean, the people from the other class probably threw them further. I'm just kidding. Let's go.
Okay, so we're supposed to measure at least 1 part to every 100. Now the distance the other group threw the marshmallows was between 24 and 25 feet, and they measured to at least 1 inch of precision. They're 288 inches and 24 feet, and that's a good precision level because that's at least 1 part to every 300.
Okay, so what you're saying is we need to measure in feet and in inches.
Yes.
Okay, I'm on it. $15, 10 inches?
15 and 10 inches.
16 feet, 6 inches?
16 and 6 inches.
17 and 7 inches?
17 and 7 inches.
And 19 and 9.5 inches.
19 and 9.5 inches.
Your instructor will introduce you and your partner to each other via email. Together, the two of you will compare the mean and spread values that you each determined for each of your experiments. How close do you think that your mean value should be in units of sigma in order for you to say that you described and conducted reproducible experiments? If the difference is larger than your requirement, brainstorm with your partner and identify the most likely reasons for the discrepancies.
Hey, thanks for helping me out earlier.
Sure. How'd it turn out?
I finally calculated our results against the results of the other group, and it turns out we were really off.
Really? Why?
Well, you're supposed to calculate this thing called sigma, and it shows how different our results were from the other students. And you're only supposed to be 2 sigmas different, but we were like 4 sigmas different.
So are you going to fail or what?
No, see, the great thing is that I read the lab manual, and it says that you don't have to be 2 sigmas off. You just have to explain why you weren't.
Okay, so what are you going to say?
I'm going to say that my partner couldn't use a measuring tape.
What? You scoundrel.
I'm just kidding. I'm going to say that the results might have been different because they threw theirs on a grassy lawn and we threw our marshmallows down a hallway. So where we were in still air, they might have had some wind effect. And also, our marshmallows couldn't scatter laterally. And my throwing arm probably isn't as good as Patrick's. And I was probably holding back because we were in a hallway and I thought that if somebody came around the corner, they would think that I was pelting them with marshmallows. You want to go get some lunch?
Yeah, let's go.
Hold on. What's natural variation?
Oh, well, natural variation is like, okay, think of 2 marshmallows, right? And between the 2 marshmallows, they have a different size and a different shape. That's natural variation.
Oh, okay. So it's kind of like my brother being really short and me being tall and handsome.
Yeah, I guess you could
Yeah.
put it that way.
That makes sense.
Could work, yeah.
Makes a lot of sense.
Okay.
I need to answer a question about measurement error.
Measurement error. I measured everything perfectly.
Measurement error refers to the uncertainty implicit in making measurements, and not to any particular person's skill with a measuring tape.
How's your lab report going?
I'm stuck on error estimates. I still don't know what a systematic error is.
A systematic error is one that affects all of your measurements in the same way, making them all too short or all too long.
So it's like I'm making mistakes. But I have a system.
Yeah, or not.
So if I'm measuring these tortilla chips, or I'm measuring the length of these tortilla chips with a ruler marked in inches, but I write down the units as centimeters, so I think that these tortilla chips are smaller than they actually are. That's a systematic error.
Absolutely. I think you've got it.
Touchdown, man! Yeah!
Now what we need to do is write down the experiment that we just did today in the
Okay.
description, so that somebody else would be able to reproduce our experiments today. Okay? Let's start describing the marshmallows that we used for it.
Okay. Well, they were white. They were Jet Puff brand marshmallows, about 1 inch in width and length, about a cubic inch, I say. Is that a unit of measure? I think it is. And they were about, I'd say, maybe 1/10 of a pound each.
What did you do in terms of measuring them? How did you do that?
Oh, we used a rigid measuring tape from the point where I stood and threw them to the
Right.
point where they landed.
Right. And some of the conditions that we had to deal with when we were out there.
Inclement, heavy weather, Hurricane Katrina. No, not really. Slight wind coming in from the west.
We were on grass.
We were on grass. It was a little bit moist.
Uh-huh.
Marshmallows got a little bit mushy.
The floor was, or the ground was
It
uneven.
was a little bit uneven, you know.
Do you think that you threw those marshmallows the hardest you could?
Look at that arm. Come on.
I'm looking at it.
Should you really be asking that?
So
Of course
was,
I did.
So was that measurement like 4 miles?
Can't remember.
You can move on to the final task of this lab, plotting the values of two measured quantities against each other and then examining their relationship. We will analyze June temperatures for various locations as a function of the sun's peak altitude, how high it appears in the sky at noon. This exercise will serve to get you thinking about how seasonal variations across the surface of this planet work and help you become comfortable making XY plots. Begin by returning to the GEAS Lab webpage and click on the link labeled Seasonal Table. This links to a page of data. A set of comments at the top of the page describes the listed quantities, and the 3 columns of numbers listed below represent the peak altitude of the sun in the sky in units of geometric degrees, column 1, June temperatures in degrees, column 2, and associated errors in degrees, column 3, for a set of northern and southern hemisphere locations across the globe. We'll ask ourselves one simple question. Are June temperatures at various locations on Earth tied to the observed peak altitudes of the sun from those locations? Read through the table and make sure it makes sense to you. Then copy the 3 columns of data by highlighting the rows in the file which contain them and typing Ctrl-C or Command-C, and return to the GEAS webpage. Click on the link for Web Application Number 2, Plotting Tool, to return to the tool which you used previously. Begin by selecting Y versus X plot with errors in Y at the top of the form from the pull-down list of plotting options. Next, type in a title for your plot and labels for the X and Y axes, keeping each label under 40 characters in length. These labels should clearly identify the contents and purpose of the plot that you're creating. You might type a title of Northern Summer Temperatures and use X and Y axes labels of Peak Solar Altitude degrees and Temperature degrees. Be careful not to reverse the X and Y axes labels. The X-axis identifies the quantity being plotted along the horizontal axis from side to side, and the Y-axis the quantity being plotted along the vertical axis from the bottom to the top of the plot. Go ahead and select Show Linear Fit to Data to cause a line to be drawn fitting the relationship between x and y values. Scroll down until you see the text box labeled Numbers to Plot, and copy your 3 columns of data into the box in the order x, y, e, or altitude, temperature, and associated error. Don't add any commas, parentheses, or other extra characters. Just place each set of 3 measurements on a separate line. Once you've completed these steps, click on the button labeled Create Plot, and your plot should appear in a separate browser window. Examine the plot carefully and make sure the correct quantities are plotted on each axis, that the error bars are present, and that both axes labels and their title are correct. Someone reading your plot should be able to identify the quantities shown and their units from the title and axis labels alone. If there are any mistakes, even small misspellings in the labels, hit the back button on your browser, fix them, re-enter your ID code, and recreate the plot. Save a copy of your plot and include it in your lab report. Be sure to include a figure caption in the report describing the primary conclusions that one can draw by examining the plot. If you're unsure what to write, imagine that you were showing it to a friend and explaining what it meant to you. Complete the remaining questions in your lab exercise, including investigating common relationships between variables, answering post-lab questions, writing a summary, and considering doing the extra credit. Note the summary of measurement methods which you may want to consult in future weeks. Consider this lab exercise a resource that you can return to help you understand experimental and data analysis work throughout the course.